So for this problem, we'll begin by, actually reading the problem. So we have a grenade that has a mass m that is projected or thrown at a speed of 51 meters per second and an angle of 40 above the horizontal. Now on its descent, it explodes into two parts of unequal masses. Now we also know that they both hit the ground at the same time, and of course the total mass is m1 plus m2, since no fragments are lost or unaccounted for. And we also know that the first fragment landed 380 meters from second fragment, 300 meters from its start. So let's actually draw a image. So we'll kind of make a graphical image. We know the scenario begins at 0.00, and then we know it's launched. So it's launched, and then it went to the max point, and then it says on the descent, so while falling down. So while falling down, it gets to some point, it explodes, and then becomes two fragments. So let's say one goes here, and then another. Now, let's fix up this part. Now what it's telling us is finding this coordinate, so x0, and also the quiz coordinate. We'll say x2, 0. And we'll say this is x1. So how do we actually get this? Now we'll begin by doing something that might not fully make sense, but let's pretend the object had actually continued on its path. So it hadn't exploded. We know that it would land right here. Alright? So, from here, we can see that the distance from the start to the end was complete, and it was completely parabolic, as we can see there, which means that this red point here signifies the range of our path. So this is the range. And then from here, we know that these two are, this is kind of less than the range, and this here is greater than the range. Or sorry, no, other way around. Greater than the range, this is less than the range here. There you go, that makes sense. So how do we actually begin by calculating? So we can use a equation that might not immediately make sense, but we can use the center of mass equation, which we know is the sum of the masses, and the positions. We begin with j equals 1, and we can also say the sum of all these masses. Right. So how does this actually help us? Well, we know that we have actually two fragments. So here we can break this down into fragment 1 and the position of that fragment, plus the grade fragment 2, plus the position of that fragment. And on the bottom, we can write fragment 1 plus fragment 2. But we also know that's the total mass of the grenade, so I'll write that as. And from there, we have a kind of equation with a bunch of unknowns. So let's start filling in a few things. So we know the masses of both fragments. So here, we know that it begins with initial speed, not velocity, so we know the magnitude is 51 meters per second. We know it's at a launch angle of 40 degrees, and that its total mass is mg. One fragment is of mass 1.1, and one is 2.1. 1 kilograms, another is 2.1 kilograms. So we know the mass of the grenade was 3.2 kilograms. And we know the second fragment landed 380 meters from the beginning. So the first one here is actually at position 380,0. And we can write here that as x1 is equal to 380 meters. So what does this leave us with here? Here we're left with, we know mf1 is 1.1, x1 is 380 plus this is 2.1. This is the unknown we want to position over, of course, we know the total mass of the grenade was. All right, now from here we have two unknowns. We don't need the center of mass, nor do we know the final position. But there's something else. We know that if the object had landed without breaking, it would land at, we'll do it in red, the range, comma 0. So what does this mean for us? Well, if both fragments broke off as an even distribution, regardless of unequal weight distribution, they're both part of the same object. So their average, or their average mass, so the center of mass, would be right here. So one lands here, but the average of the two would be here. So what does that mean for us? Well, that means that our x center of mass, or the position of the center of mass, is the same as the range. So here we can say that r is equal to that. But I will keep it in variables for now. We'll delete this. And we know this is equal to r. So if you want to isolate for this variable, let's rearrange. And we get that x2 is equal to r mass of the grenade minus the fragment 1 and its position all over the fragment 2 mass. Alright. Now from here we can kind of further complete this equation by actually bringing the range. So recall that range is equal to initial velocity squared over g times sine 2 theta. And we actually have all of that. Sine 2 theta. And we're going to break the fraction just for the sake of looks, I guess. And then this would be m grenade over the fragment 2. And then this would be minus fragment 1 over fragment 2 times position 1. Now we can plug in everything. So now here we get that initial velocity was 51. This is 9.8. This is sine of 80. Mass of grenade is 3.2. Fragment 2 is 2.1 minus 1.1 over 2.1. And this position was 380. From there, we can get a final position, 80, and make sure it's in degrees, because that'll mess up everything. 2 over 2.1 minus 1.1 over 2.1. So we get negative 191.2380649. Now why is it negative? Did I square? Oh, that's why. Yep, I didn't square the velocity. There. So this is instead initial velocity squared. Let's see if I messed up anything else. 2 times 40 is 80. Mass of grenade over m fragment 2. Yep. M fragment 1. We know 1.1, 2.2. Yep. And yeah, that should be good. So we actually get 199.2396448 meters. And that should be our this position here. So that should be, we'll say, could we go to 200? No. 199.0.